ones are a special kind of matrices actually, and well, this is a joint work with my student Yuichiro, still just right there. And actually, most of the mathematics and network and all the calculations and whatnot were done by my students. So I don't want to steal her credit. So I'll only talk about a little bit of background here. And so the most important things will be given in the next task actually. So you can maybe you should come back later in maybe 20 minutes or so. Okay. Okay, so X codes are very special to me because I learned about X codes when I was visiting Arizona State University when I was a student, and it was like more than a decade ago, I think. And so it's very I'm very happy to be able to give a talk about X codes at this conference. So X codes is, like I said, is a binary matrix which is used for a special kind of VLSI testing, and we are going to use this matrix as a linear map to compress a certain very big data. So maybe you may have a million bits or a billion bits, and you want to start to finish on the very long vector, but you don't want to do that. So because it's time consuming or it's very expensive, so you what you do is to take a linear map of the long vector and B where M is the X code, so that you can work on the hash one. So what we really want to do is comparing two vectors. Before we talk about the details of X codes or where X codes are used, we first talk about the simplest case of comparing two vectors. Say you have one binary vector called V, which we call reference, which is supposed to be the correct one, so the golden reference. And you also have another binary vector, let's call it W, which should be equal to the reference vector, but could be wrong. So there might be some discrepancies between V and W. So if V and W also are very small and contain, say, only 100 bits, then you can just compare V and W bit by bit. But if V is very long, or you do not have enough time to do a bit by bit comparison, then just a simple comparison is infeasible. So in such a case, one standard method is to take hashing. So it's just probably you are already doing this kind of thing every day, like when you download the data and check the check bits of the download data, and so if your downloaded data is correct. So it's the same thing, and so if direct comparison is infeasible, you may just compare the shorter ones, hashed bits. In our case, we use a linear mapping to hash long data. So we have binary matrix M, which we will use as an X code. M has to be a fat matrix, so you have many columns, maybe a million columns or more, but only have a few rows, or it could be hundreds or so, depending on your applications in mind. But the important thing is that you have much more columns than rows. And V is a long reference vector, which is always correct but too long. And the length of V has to be the same as the number of columns of M. And W is the one which is supposed to be the same as V, but could be wrong. Okay? So we check instead of V and W directly, we check whether the product between M and V equals the product between M and W. It should be easier if we only have few rows, because this is just taking, let's say, a syndrome or just taking linear map. But it's, of course, this is in a sense imperfect, because the size of the space of V is, if you are working on n bits, then and it's binary, then it should be 2 to the n. So the dimension is n, so you have 2 to the n vector possible reference vectors and W. And if m only have, say, 100 bits, which then you only have 2 to the 100 possible vectors as an outcome. So there has to be a collision between MV and W, even if V and W are completely different. So when we impose the condition we impose on the V and W is this: if we want to make sure that if V and W have at most a certain number, say D, discrepancies between them, then we want to detect them. In this case, well, the problem becomes exactly the same as, say, detecting errors by using a linear code or a standard group testing problem, because in the previous slide we have MV and MW, and these guys are different as long as V and V have at most D discrepancies, and M forms a parity check matrix for a linear code of V1 distance at least D plus 1. Well, this is maybe obvious, because if M gives you a linear code of V1 distance at least D plus 1, then any D or fewer columns are linearly dependent. So you always have different, in a sense, syndromes. However, in the case of Xcode, we have another condition which makes the problem more difficult. So we have to handle what we call unknowns or unpredictable bits. In this case, certain bits in the reference vector V are unknowable to you. So they could be just random bits, or they could be not random, but you don't know anything about it. So we just mark them by X. And X is not a variable. It just means just a symbol which represents that you have no information here. Okay. So if the reference vector V has X somewhere, then what happens is that when you take some linear combination between the bits among the bits of V, then there will be many x's in the resulting hash vector, because x plus something, either 1 or 0, becomes again x, because x just means you have no information about it, and so x plus something is again just you don't know. So you can only reliably tell that x times 0 equals 0. but x times 1 or equals x and x plus 1 or x plus 0, again, we don't know anything about it. So if you represent the matrix as a binary, if you represent the binary map as graph like this one, so here, if you represent 3 by 8 binary matrix like this one, and here we have an edge here because the first bit will be hashed to this guy with these two guys and taking order of 2 here. And if you have an x here, then this particular linear map will result in x here. And if x is here, then this guy goes to 0 and gets mixed up with 0 and 1. And so this guy will be okay, x. And if your matrix demands you to this bit to go to here as well, then this guy becomes x as well. So all 3 bits will be x again. So you have no information in the resulting hashed vector. So if there is an x in the reference vector, you shouldn't have many edges here because it will propagate x in the resulting vector. So the problem I was given by Professor Coleman 10 years ago was like this one. It was it was about the technique invented by, I believe, Intel, and it is called X-compact, and probably my students will give the detail of the background. So I will stop here and just show you some interesting results. But the point is that the reference vector V contains x's, and the vector W should be checked. It's also binary, and it doesn't contain x. And these x's in V must be put into the compactor, which means you have to put x's into the. You have to use these x's when you hash the long vector. Of course, if you do not need to do this, then you can just ignore x part and just use the shorter vector, and maybe you can just compact hash it by using some another matrix and do the same thing, and you can compare the hash bits reliably. But in the particular case of X-compact, you have to input x's into your linear hashing. So the problem becomes, how do we ensure that the hashed bits NV and W exhibit discrepancies when there are certain number of unknowables and at most D discrepancies between V and W? Okay. And so this is the answer, and the matrix M should be an X code which is defined like this. The X code, which can be used when there are some x's, is n by n binary matrix in which the superimposed sum of any x column does not correspond to sum of any other D or fewer columns. So if there is no condition like this one, then it's just parity check matrix for a linear code with minimum distance at least d plus 1. Into n bits, we want to n as small as possible and n to be as large as possible. So you can formulate a mathematical problem like this one. For example, if you fix d, x, and m, you'd like m to be as large as possible. And so, for example, we can consider an upper bound on the largest possible n, and I believe my students will give many results and excuse me. So results and which will improve on the previous result, which me and Charlie Colborn proved like 10 decades, 10 years ago. So I hope my students' results will not make me look dumb. But anyway, so I'll just explain one little cute result. And so the result is about a special case. Here we consider m and dx code of constant column weight. Okay, so we also impose another condition that the binary matrix for hashing has to be equal weight, and the weight should be 3. Okay, in this case, it's very simple, and it's interesting because, well, of course, there is an engineering reason why we have to consider the constant weight column. But more than that, when I was a student, I was very interested in the Steiner triple systems, and in this case, if they put d equal 1, mn1 x goes of constant weight 3 is actually the best one corresponds to the Steiner triple system. So that was why I was very interested in this problem in the first place. But anyway, we consider the case when constant column weight equals 3. In this case, the known results say that the largest possible n should be small theta n squared when x is also, I think, 4 or 2 probably. 2. Okay. Thank you. And so this is a known result, and this is because the best possible x code when x equals 2 or constant weight 3 is actually Steiner triple system or maximum packing, maximum triple packing. So you can't have more than this number, but you are sure that you can achieve, say, when n is continuous to 1 or 3 modulo 6, you can have this number of columns, because there is a Steiner triple system of order n, and you can just use the instance matrix, point by block instance matrix as an x code. But what if we fix x equals 2 and increase d to, say, 2, 3, 4, 5, and so on? When I was working on this problem first, we couldn't prove anything about the upper bound. However, about a year ago, I think last year, my student was giving a talk on this problem in Japan, and at that time, one student, I think now a former student of Professor Miao, was there, and she realized that this problem is very close to her problem, and she suggested us to apply this particular lemma in extreme graph theory, which is called graph removal lemma. And this is a very, very interesting lemma, it seems, and she applied to her problem and got a very nice result. And also, I believe that she gave me a paper written by Professor Gay and I believe his students, where this lemma is also applied to obtain upper bound of a certain combinatorial structure, which is very similar to X-code in a sense. And we worked on this lemma, and we have to tweak how to apply the lemma a little bit so that it works very well for this particular problem. But we actually was able to prove that the n should be small O of n squared when b is greater than 4. This is when b equals 1. So in 10 years ago, I couldn't prove anything about the constant weight X codes, and I accepted some constructions of that. But when it comes to the upper bound, I only had this rather trivial one. But now, by using some more recent mathematics, I would say, actually my student did it. We were able to prove this kind of tighter upper bound. So, and this, I and my student will be able to do that without the help of Professor Miao and the former student. I think she is now a postdoc in Israel, and I also read Professor Gay's paper, and in the next talk, you will hear a lot of progressive combinatorics, hopefully, and my students learned it from papers written by Douglas Stinson. So about cover-free family is because cover-free family is very, very similar to X-codes. And so, so thank you everyone here, and thank you, many people who wrote interesting papers which led me to this particular result. And so, and also thank you, Charles Carbon, especially because this all started when I visited Arizona. So happy birthday! Thank you.
Any questions or comments? Okay, no question. Let's thank the speaker again.